Welcome back to ControlX Automation. I'm Akhil, and in today's video, we are diving into functional safety with a hands-on look at ISO 13849 safety categories. If you've ever wondered what actually separates a Category 1 safety circuit from a Category 4, or how those definitions in ISO 13849 translate into real wiring on a machine, then this video is for you. In this tutorial, I'll break down the safety categories in plain language, then move from theory to practice by wiring a real Category 4 safety circuit using a safety relay, an emergency stop push button, and motor contactor, so you can see exactly how functional safety is implemented in the real world. This video was made possible with the support of industrial automation distributor and solution provider Advanced Motion and Controls, who supplied the safety relay from Euchner featured in this video. Before diving into the engineering, I want to lay the groundwork first by introducing the safety standards. Global safety standards for machinery are governed by these two organizations, ISO and IEC. ISO is short for International Organization for Standardization. ISO develops and publishes globally recognized standards across a wide range of technical and non-technical domains, including manufacturing, quality management, food safety, transportation, agriculture, and healthcare. More specialized areas, particularly those involving electrical, electronic, and electrotechnical standards, are handled by IEC. IEC is short for International Electrotechnical Commission, and it is a global standards organization responsible for developing and publishing international standards for electrical, electronics, and related technologies. IEC covers electrotechnical standards, and ISO covers all other standards. Machinery safety standards are written by working groups comprised of experts from many member countries. Regional and country-specific standards continue to support local requirements, but in many countries there has been a move toward using the international standards produced by ISO and IEC. Functional safety and performance levels are key elements behind the machine safety standard ISO 13849. Being a global harmonized standard, it is accepted worldwide in designing the safety-related parts of the control system of a machine. Safety devices are designed to fail to a safe state. However, there exists the possibility of failing in a dangerous state. Functional safety, as defined by the ISO 13849, looks into minimizing this possibility, as we will explore later. ISO 13849 uses performance levels, or PL, to categorize the level of safety on a machine or control system. The standard defines 5 levels from A to E. PLA represents the lowest safety level, while PLE is the highest and most rigorous safety level. The standard evaluates the achieved PL of a safety function using 4 core parameters. Category describes the physical wiring of the safety circuit, and it's further classified into 5 levels: B, 1, 2, 3, and 4. Higher category means more redundancy and fault tolerance. Category 4 is required to achieve PLE. This is a measure of how effectively the system detects internal faults. For the safety function to perform as expected, requires a calculation to prove its effectiveness. High diagnostic coverage is required to achieve performance levels D and E. MTTFD is the mean time to dangerous failure. This element measures the hardware reliability and is expressed in years. Components might experience wear and tear that can push a system beyond its mechanical limits. Thus, calculating the MTTFD provides an estimation of when a device may have higher probability of experiencing a dangerous failure based on its usage. CCF is a term that refers to failures of different components resulting from a single event, where these failures are not consequences of each other. An example could be a short circuit that causes a contactor to weld and simultaneously takes out the safety relay that controls the contactor. Its purpose in the evaluation of performance level is to prevent a single event from defeating the safety system by implementing redundancy. In this tutorial, we'll learn about these various categories, and then I will show you how to design and implement a Category 4 machine safety using a safety relay. In industrial automation, we often hear the term functional safety. It is the part of a safety system designed to reduce risk by ensuring that control systems behave correctly in response to inputs, particularly to prevent hazardous events. It is often referred to as the safety-related control system, or SRCS for short. When a hazard cannot be removed by design and physical safeguards like fences and fixed guards are not sufficient or practical, we must rely on the control system to reduce the risk. This SRCS is the combination of hardware and software that perform the safety function. The reliability of this system must be proportional to the level of risk it is mitigating. Functional safety is the part of the overall safety requirement, and that depends on the correct functioning of the process or equipment in response to its inputs. For example, an over-temperature protection device using a thermal sensor in the windings of an electric motor to de-energize the motor before it can overheat is an instance of functional safety. Now let's understand the system architecture for an SRCS. This illustration shows a typical SRCS, which can be split into basic system components or subsystems. Each subsystem has its own function. At the fundamental level, the subsystems can be categorized into three basic functions: inputs, logic solving, and actuations, which is the output subsystem. This is generally referred to as the ILO loop, ILO being input, logic, and output. Some simple systems may not have the logic solving stage, and in those cases, the inputs directly impact the outputs. In this example, the inputs can be primary safety devices like a door interlock switch or secondary safety devices like e-stop push buttons. The logic can be handled by a dedicated safety PLC, or as in this case, a safety relay or controller. A safety relay plays a crucial role by constantly monitoring its own inputs for faults, short circuits, cross-monitoring, and other discrepancies. A standard PLC with non-safe I/O does not do this. In case of dual input signals, the controller compares the two input signals, and if it does not match, it switches to a safe state. In order to enforce the safe state, actuators are connected to the outputs of the safety relay, which force the state of the machine to a safe state by either opening contactors to remove power from the system or command the VFD to stop the motor, thereby eliminating the motion hazard. The main idea for implementing functional safety is risk reduction. The red stacks represents the unmitigated risk in the machine or process. By implementing appropriate safety measures, the risk has been reduced as represented by the smaller green stack. This is the purpose of designing a high-integrity SRCS, to make this residual risk as low as reasonably practicable. Next, let's dive into the safety categories that I mentioned earlier. This directly impacts the electrical control circuit design for the functional safety implementation. When designing an SRCS, we use designated architectures known as categories. These categories, ranging from B to 4, define how a system is structured to resist or detect faults, whether there is redundancy or not, if it is single channel monitoring or dual, whether there is diagnostic testing or self-monitoring, and other factors. This infographic provides a quick overview of the 5 categories and their contribution to the performance level. Let's start with the basic safety category B. This is the architecture for a category B safety system. This category provides the basic requirement of any control system, whether it is safety related or non-safety related. Category B forms the foundation upon which other categories are built. At the heart of it is a logic device that processes the inputs and controls the outputs. The logic device could be a PLC or a simple safety relay. Here's an example of a simple category 1 control system. This is a single channel design with no redundancy, has no diagnostic coverage, no self-checking, no fault protection. So if a fault occurs, like a broken wire or welded contact in one of the push buttons, the system has no mechanism to detect it. The performance level achieved under this category is PLA or B. Under this category, the control system must be designed using best engineering practices such as NEC or NFPA and built using basic safety principles as defined in the ISO 13849 standard. The designer must select, install, and assemble according to the manufacturer's recommendations and instructions. The control system must be designed to operate in its expected environment. For example, size the components to the correct voltage and current requirements. Designer must also ensure electromagnetic compatibility and consider physical environmental conditions like ambient operating temperature, humidity, vibration, shock, etc. When using relays and contactors, implement adequate transient protection so we don't get spikes when a coil de-energizes. Many modern switching devices have built-in protection, so check the datasheet and design accordingly. Implement overcurrent, overload protection devices like properly sized fuses, breakers, motor overloads, etc. So you may ask, when is category B acceptable? Only when the risk assessment per the ISO 13849 determines that the required performance level is PLA. This applies to machinery with very low severity consequences and infrequent exposure to a hazard. Category 1 carries all requirements of Category B and adds one critical constraint. The SRCS must be designed using well-tried components and well-tried safety principles. ISO 13849 defines well-tried components as those that have been widely used in the past with demonstrated successful performance in safety applications, and demonstrated suitability and reliability for safety-related use. Well-tried safety principles include things like positive mode actuation, using force-guided relays, spring return mechanisms, and redundant fastening. This is also a single channel design architecture, has no diagnostic coverage and no self-checking or fault detection. So if a fault occurs like a broken wire or welded contact, the system has no mechanism to detect it nor respond to it. However, in this case, well-tried components and well-tried safety principles are used. Category 1 is intended to prevent failure by using well-tried components with high reliability. Thus, the performance level that can be achieved with this category is PLC. So when is category 1 acceptable? This is suitable for low to medium risk scenarios where the probability of hazard exposure is low and consequences are limited. Category 2 carries all requirements of Category 1 and introduces a fundamental new concept. The safety function must perform self-checks and monitoring at suitable intervals. These checks, called automatic tests, must be executed by a test channel called OTE, which is short for Output Test Equipment, and must be separate from the safety channel. For example, monitoring the feedback of the output relay or contactor. This helps the logic device detect failures on the output devices and provides some diagnostic coverage by detecting dangerous failures and reacting to them, typically by disabling its outputs and putting the system in a safe state. These test signals must occur at frequency appropriate to the risk, typically at machine startup or periodically during operation. ISO 13849 stipulates that the ratio of test frequency to demand frequency must be greater than or equal to 100 to maintain the integrity of the category. The safety function must be able to drive the system to a safe state if a fault is detected. If no faults are detected, the machine is allowed to run, but if faults are detected, a fault reaction must ensure that the machine remains in a safe state. This category requires the use of safety PLC or safety relay, and the maximum PL achievable with category 2 is PLD. When is category 2 acceptable? This is suitable for applications where periodic verification is practical and the risk level doesn't demand continuous fault detection. A practical example would be safety light curtain with a muting function that performs a self-test on startup. The OTE channel monitors the output device like a contactor via auxiliary feedback contacts before each machine cycle is permitted. Now we are getting into serious safety systems with category 3. This carries all requirements of previous categories and introduces redundant dual channel architecture. This means now there are two independent channels and both must agree. The system is designed so that a single fault does not immediately lead to the loss of the safety function, which is the case with lower categories with single channel inputs. Redundant components significantly reduce the probability of a dangerous failure. Consider a category 1 control system with an e-stop which has a single NC contact. When the operator hits the e-stop during an emergency, if the single contact fails while pressed, the SRCS has been compromised and the system is no longer in a safe state. In a category 3 system, the implementation of dual channel redundancy drastically drops the probability of dangerous failure. A single fault in either channel does not defeat the safety function. The redundant channel maintains it. The defining requirement is that a single fault in the SRCS shall not lead to the loss of the safety function. And like before, there is still self-checks and monitoring of the safety function. Monitoring increases the chance that faults are discovered before demand. This is a practical example of a Category 3 SRCS implementation, showing a dual-channel e-stop wiring. Here we have two independent signal paths from the e-stop push button feeding two independent input channels on the safety relay. If one channel opens due to a wiring fault or contact failure, the safety relay detects the discrepancy and either maintains a safe state or flags a fault depending on the relay's monitoring implementation. In both cases, the safe state is maintained by opening two internal dual-channel NO relay contacts. The force-guided output relays K1 and K2 directly support this architecture. Their mechanically linked contacts ensure that if a contact welds, the mirror contact cannot close, making the fault detectable. When is Category 3 acceptable? It is commonly used in industrial machinery with moderate to high-risk applications. Depending on other factors like MTTFD and diagnostic coverage, the maximum achievable performance level is PLD. Finally, we have Category 4, which has the highest integrity with full fault tolerance. Category 4 differs from Category 3 in that it has higher diagnostic coverage than Category 3. This carries all requirements of Category 3 and removes its key limitation. The standard requires that a single fault shall not lead to the loss of the safety function, and the single fault shall be detected at or before the next demand on the safety function. If this detection is not possible, an accumulation of faults shall not lead to the loss of the safety function. In practice, Category 4 demands dual-channel redundant architecture, which is the same as Category 3, and high diagnostic coverage greater than 99%, which means nearly all dangerous faults must be detected, and high MTTFD on each channel. Thus, this results in an architecture with two fully independent redundant channels, continuous cross-monitoring between the two channels, output monitoring elements monitored via feedback, typically through EDM, which stands for external device monitoring, using auxiliary contacts of output contactors and relays. And fault detection must be continuous and comprehensive and not periodic. This is why force-guided or positive-guided relays are mandatory in Category 4 output stages. Their mechanically linked mirror contacts make the welded contact condition detectable through the EDM feedback loop. A standard relay cannot provide this guarantee. This kind of relay have forcibly guided contacts in which the NO and NC contacts are mechanically linked, so they cannot move independently of each other. If this relay coil energizes or de-energizes, all contacts must move together as a single mechanical system. This mechanical interlock is the entire point. A standard relay can fail silently, and a welded NO contact might stay closed even when the coil drops, and you'd never know. A force-guided relay solves this problem. If one contact fails, the others reveal the failure. You may ask, how are we able to achieve high diagnostic coverage in Category 4? Let's look at this diagram, where we are monitoring two NC contacts of an emergency stop push button using dual redundant channels of the Category 4 monitoring safety relay. Here we can see the diagnostic monitoring on both channels by means of test pulses. Each channel has its own test pulse, which it expects to see on the corresponding inputs. During a normal e-stop activation, when the button is pressed, both NC contacts open simultaneously, and the monitoring safety relay treats this as a e-stop button press and de-energizes its internal relays, which in turn puts the machine in a safe state. Next, let's explore some common failure scenarios that could happen in real-world situations. Consider this scenario where one of the contact has failed, which could either be a welded or stuck contact, or a mechanical failure of the contact, or even intentional tampering, like bypassing a contact. When the e-stop button is pressed, we have what is known as a mismatch condition, and this leads to a safe state. However, the safety relay will not be able to reset until the fault condition is rectified. How about a broken wire? Now input A notices the missing test pulses and immediately triggers an error condition, switching their safety relay to a safe state. Another failure condition could be one of the channels is shorted to ground. In this example, input B is shorted to ground, and this causes the safety relay to switch to fault condition, which triggers the safe state. Now that we have seen the various failure conditions, I will set up a demo on my desk and replicate these conditions to see how a Category 4 circuit implementation can keep the system operating safely. In this part of the tutorial, I'll show you how to implement a real-world Category 4 PLE safety circuit using an Euchner ESM safety relay, which is provided to us courtesy of Advanced Motion and Controls. The ESM safety relays are available in various configurations and applications. I'm using the ESM BA301 variant, which is suitable for use up to Category 4. Key features of this variant are it has two green LED indicators which indicate the switching status of the two internal relays. It features both single or dual channel control, suitable for use with e-stop push buttons, safety switches, as well as safety devices with OSSD outputs like light curtains. It has three safe redundant relay outputs with contact rating up to 15 amp cumulative current, which is the maximum combined switching current through all three safety contacts. Also has one auxiliary NC contact which is electrically isolated from the NO contacts and can be used for monitoring or indicating purposes. It features ground fault monitoring to detect short circuits between the connecting wires and ground. This will immediately switch the outputs to safe mode and prevent relay from restarting until the fault has been resolved. This relay can be wired for either automatic start or manual start. The actual implementation will depend on your application requirement. And this relay comes in 3 voltage variants. The one I'll be showing you will be the 24 volt version. This relay is designed for mounting on 35 mm DIN rail. Dimensions are as shown. All electrical connections are made via screw terminals which are labeled. For more information, here's the link to the product page for this relay. This image shows the internal block diagram of the ESM BA301 safety relay and the connection terminals. External 24 volt power supply is provided to the relay via terminals A1 and A2. Input safety connections like e-stops, safety switches, as well as the restart button in case of manual start option are connected to these terminals. I will show the exact connection layout shortly. There are 3 safe redundant outputs and can be used to drive loads up to 15 amp combined. Finally, terminals 41 and 42 are the auxiliary NC contact and can be used for monitoring or indicating purposes. This is the setup I'll be using for the hands-on part of this tutorial. Here I'm showing 2 output contactors K1 and K2 which are used in a motor circuit. However, I only have one contactor, so I'll be demoing with just one. Let's get to it. Okay, e-stop pressed, it should not reset. Okay, so now we pull the e-stop out. So to simulate, we jumpered one of the contacts and our contactor is in. Okay, hit the e-stop. So that brings our machine to a safe state. Now we should not be able to reset until the problem is fixed. That doesn't reset it. So we are still in a safe state. Okay, so the short circuit has been resolved, or the welded circuit has been fixed. And it's reset. And now we are back to operation. Okay, wire's broken. It should not reset now. Okay, so wire is fixed. You have to do the E-stop again. Okay, perfect. So right now relay is good. Contact is closed. We're going to simulate. Okay, that E-stops it. Now if you keep holding it to ground and try to reset with the other hand. Yeah, it should not reset. So we have to clear the fault. Yeah, now it should reset. Thanks for watching. If you found this video helpful, then please like and share. If there's a particular topic you want to see me cover, then please drop your suggestions in the comments. And be sure to subscribe so you don't miss out on future content.